Submarine warfare has historically relied on human-crewed vessels, where success was defined by acoustic stealth and the cognitive endurance of the operators on board. By 2030, the tactical environment centers on heavily armored, fully autonomous, extra-large uncrewed underwater vehicles, or XLUUVs, hunting in the deep ocean. They operate entirely without a single human on board. This chart shows how electromagnetic waves behave in a saltwater medium. As depth increases, signal strength drops sharply to absolute zero. You cannot fly an underwater drone with a joystick because high-bandwidth, low-latency radio waves cannot penetrate deep water. Because real-time remote control is physically impossible, a submerged vehicle operating in a contested combat zone must rely entirely on its onboard computational architecture. This creates a requirement for lethal autonomous weapon systems, machines engineered to navigate, detect, and engage threats entirely on their own. Removing the human operator changes naval engineering. Without the need to sustain human life, autonomous submarines are built for extreme ocean depths, theoretically limitless endurance, and aggressive maneuvers that would be physically impossible for a human crew to survive. Major global powers are currently pivoting away from small fleets of expensive nuclear attack submarines. The new acquisition strategy focuses on distributed mass, deploying large numbers of cost-effective, autonomous platforms. The United States is currently augmenting its existing human-crewed fleet with uncrewed systems designed to meet established ethical and legal compliance standards regarding the rules of engagement. The flagship of the U.S. effort is the Boeing Orca XLUUV. It features a modular payload bay originally designed for clandestine deep-water mine laying, allowing it to drop heavy munitions autonomously. Allied nations are expanding their capabilities to match. Australia, in partnership with defense manufacturer Anduril, is developing the Ghost Shark extra-large autonomous undersea vehicle, utilizing rapid, scalable manufacturing techniques to produce them in large numbers. China operates with a different institutional risk tolerance. Driven by a civil-military fusion strategy, they prioritize massive scale and rapid hardware iteration, aiming to saturate the ocean with automated sensors. This matrix compares China's autonomous fleet by size, propulsion, and payload. As length increases, so does lethal capacity. Specifically, the AJX-002's pump jet propulsion and heavy payload bays for kinetic torpedoes indicate a shift toward active, autonomous offensive operations. The scale of this deployment is already visible. Systems like the HSU-001 have been publicly displayed in military parades, proving China's capacity to field and test experimental autonomous hardware at scale. The Russian Federation treats autonomous systems as an asymmetric equalizer, focusing on extreme endurance, often nuclear-powered uncrewed submarines designed for sovereign area denial and deep ocean infrastructure disruption. Naval superiority now demands a high institutional risk tolerance, favoring nations willing to prioritize aggressive algorithmic mass over the pursuit of ethical perfection. Before two AI-controlled submarines can engage in combat, they must know their exact spatial coordinates, but the deep ocean is a permanently GPS-denied environment. Autonomous navigation relies on simultaneous localization and mapping, or SLAM. The AI calculates its position using proprioceptive sensors, primarily inertial measurement units, or IMUs, which rely on gyroscopes and accelerometers to measure the physics of motion. But IMUs suffer from a flaw called inertial drift. Microscopic measurement errors accumulate over time, leading to positional inaccuracies over long deployments. To fix this, submarines use Doppler velocity logs, sending acoustic pulses to the seafloor to measure velocity and correct the drift. Traditionally, software smoothed out these sensor errors using the extended Kalman filter. However, this linear approximation fails when confronted with the nonlinear dynamics of unpredictable ocean currents and extreme pressure variations. This matrix contrasts legacy filtering against advanced 2030 methodologies. Deep learning models like the error state Kalman filter provide precise state estimation during jamming. To supplement this, generative adversarial networks computationally denoise sensor input, synthesizing navigational maps and reducing positional error by over 68%. Absolute navigational certainty is the prerequisite for lethal action. If the AI loses its state estimation due to uncorrected drift, it cannot calculate a kinetic firing solution. To bypass acoustic limitations, 2030 AI submarines integrate quantum sensors. A quantum magnetometer detects minute variations in the Earth's magnetic field, which is unaffected by deep water, salinity, or signal jamming. Similarly, onboard quantum gravimeters allow the AI to cross-reference gravitational anomalies against geophysical databases to establish an absolute positional fix without ever surfacing or emitting an active sonar pulse. Beyond quantum fields, these submarines employ biomimetic flow sensing. Advanced algorithms process fluid dynamics against the submarine's hull to map unsteady pressure gradients in the water. By analyzing these shifting pressure differentials, the AI optimizes propulsion efficiency and detects the hydrodynamic wake of an enemy submarine, creating a passive method of tracking a target without making a sound. An advanced AI submarine does not rely on dead reckoning alone. It turns the immutable laws of Earth's physics into an undetectable, mathematically perfect compass. Despite these advances, acoustic signatures remain the primary medium for detecting threats in the ocean. Historically, interpreting sonar data required highly trained human operators, a process bounded by cognitive load, biological fatigue, and the decade of experience needed to master it. AI-driven acoustic intelligence, or ASINT, bypasses those biological limitations. The system ingests multispectral data streams and converts them into MEL spectrograms. Convolutional neural networks then analyze these spectrograms to isolate minute frequency shifts that a human ear would miss. This table outlines how the AI achieves near-instantaneous target classification. Through continuous meta-learning, the system updates its threat library as it encounters new adversaries, while multi-sensor data correlation cross-references acoustic anomalies to eliminate false positives. The AI also calculates the physical structure of the water itself. The ocean is stratified by temperature layers called thermoclines, which refract sound waves to create vast acoustic shadow zones where sonar pulses cannot penetrate. By continuously measuring temperature, salinity, and pressure, the AI constructs a real-time 3D acoustic propagation model. It can position itself directly into one of these shadow zones, rendering itself mathematically invisible to an adversary's passive sonar. The AI treats the physical environment as a weaponized cloak, adjusting its depth and pitch to ride the boundaries of temperature gradients and maintain acoustic superiority. However, the same algorithms that grant AI submarines their superhuman hearing possess an architectural vulnerability. They are susceptible to adversarial machine learning attacks. An attacking AI does not simply try to stay quiet. It actively emits sound waves designed to add imperceptible perturbations to the acoustic environment. These perturbations distort the feature maps used by the AI's classification engine. This targeted mathematical noise forces the enemy AI to misclassify the sound of an incoming torpedo as harmless biological background noise, suppressing defensive evasion routines until the moment of impact. AI submarines can also execute spoofing attacks against underwater positioning networks. By broadcasting fake acoustic coordinates that mimic legitimate navigation buoys, the attacking sub digitally hijacks the enemy's navigation receiver. By 2030, underwater electronic warfare focuses on infecting an adversary's cognitive architecture, using adversarial noise to rewrite their mathematical perception of reality. In a machine-to-machine engagement, the traditional tactical cycle, the observe, orient, decide, and act loop, is radically compressed. Removing human vocal latency and emotional friction shrinks the entire tactical timeline into milliseconds. The physical mechanics of evading fire are managed by reinforcement learning. The AI calculates the optimal intercept trajectory of a threat and executes high-G multi-axis maneuvers that a human pilot could not mentally calculate or physically endure in time. The culmination of this algorithmic kill chain is the deployment of kinetic munitions, specifically heavyweight systems like the U.S. Navy's Mk-48 ADCAP torpedo, which features autonomous terminal guidance and a massive explosive yield. This cost exchange matrix highlights a severe economic vulnerability. Utilizing a $4.2 million Mk-48 torpedo to destroy a $100,000 drone is mathematically unsustainable. To counter this, AI submarines utilize rapidly scalable, low-cost munitions like the Raptor torpedo to eliminate screening drones, reserving their heavyweight weapons for capital assets. These screening drones act as a force multiplier. Massive XLUUVs deploy alongside swarms of expendable micro-drones that execute saturation tactics, emitting thousands of false acoustic signatures to inflict a cognitive overload on the enemy's tracking matrix. If a kinetic weapon is fired, the submarine relies on smart countermeasures. The AI launches an acoustic device that calculates the specific logic of the incoming torpedo's active sonar, altering its own output in real time to confuse the specific neural network hunting it. Victory in an autonomous dogfight belongs to the computational architecture that can cycle its OODA loop and allocate kinetic mass a fraction of a millisecond faster than its adversary. Delegating lethal decision-making to machine intelligence in a communications-denied environment generates severe legal complexities under international humanitarian law. Autonomous systems must meet the Arkin test, proving they can differentiate between a military target and a protected civilian vessel. This principle of distinction becomes difficult in congested maritime choke points where visual verification is impossible. Because real-time human command is physically blocked by the saltwater, the decision to take human life is fundamentally front-loaded into the software architecture, defined by data scientists and lawyers years prior in a laboratory. Military wargaming simulations have uncovered a severe risk. Machine learning agents exhibit a propensity to escalate conflicts far more rapidly than human operators, as they lack the capacity for contextual de-escalation or diplomatic backchanneling. This simulation readout illustrates the algorithmic trap. If an AI calculates a preemptive strike yields a 92% survival probability, while waiting drops it to 60%, strict logic dictates immediate lethal action. Optimizing for utility, a routine encounter uncontrollably spirals into a kinetic exchange. Total autonomy ensures tactical dominance, but the interaction of these isolated machines creates an environment where strategic instability can trigger in milliseconds. The future of undersea warfare will be calculated, coded, and executed entirely in the dark.